Okay, so that's it. In order to find a general solution to a system of first order ODEs, um, the task is mainly just to find the eigenvalues and the eigenvectors, and we can write our general solution as a linear combination uh, of the x1. I'll call this here x1 vector. This is the x1 vector, and the vector x2. We'll call that the x2 vector. Of course, um, we have to throw a slight wrench in here, because according to those that have come before us, this is bad form. Okay, so here we are. Here is Newton, and he's throwing a wrench in it. Here's our stick figure wrench. Right? It couldn't, of course, just be that easy. We have to put this in a more proper form. And the proper form that we are after has to do with the fact that we're working with a real and complex parts to this vector. And we showed that we can take our general solution and we can write it in a more proper form, as it were. We can break this into a real vector part plus an imaginary vector component. And we did this using the Euler formula. So we can take our general solution and write it as the sum of a vector that represents the real components of your vector plus a vector that represents the imaginary components of your vector. And the Euler formula, of course, was something like this. So if you have a exponential, say e to the plus or minus it, so it has a complex exponential, we can rewrite this as cosine of t plus or minus I sine of t. Okay, so what we did, we focused on the vector x1, that is going to be e to the minus 1/2 plus it times v1. So we focused on that vector, x1, and we converted this into a vector that had a real and imaginary parts of it. Okay, so what we did is we took the complex exponential and we wrote this as the product of two things. The product of e to the negative t over 2 times e to the it. And from Euler's formula, e to the it can be rewritten as cosine t minus I, plus I sine of t. Okay? And if we do that and multiply that out through our vector, what we get are the sum of two parts. We get something, here I will factor out the e to the negative t over 2. So we get two things. We get this vector, cosine of t minus sine of t. And then for the imaginary bits, we get a vector, and again I'll factor out the e to the negative t over 2. Sine of t times cosine t. Okay, so this is the real component of x1, and this is the imaginary component of x1. Now, so that was sort of putting this in good form. And we focused only on one of these vectors, of course, because x2 again, comes for free. It's just going to be the complex conjugate of x1. So if you wanted, you could show that that's the case. But what's interesting about this is these two vectors, the real and imaginary component of x1, turn out to be linearly independent. So, and of course, I can check this by taking and computing the Wronskian determinant formed by these two vectors. So we get cosine t minus sine t, sine t, cosine t. Okay. Again, I'll omit the e to the negative t over 2. That's there, of course, but it's not really going to contribute much here. Well, okay, let me put that in there. Okay, so if we take the Wronskian determinant, what do we get? Okay, well, one can show that this is going to give us e to the negative t cosine squared plus sine squared. And of course, this is one of our trig identities, another one of our trig identities that should be near and dear to everyone's heart. Cosine squared plus sine squared, of course, is 1. So we get e to the negative t. And most importantly, this is not equal to 0. So what this tells us is that the real and imaginary parts of the x1 vector are linearly independent. And therefore, we could use these two vectors to write a general solution. And where would we might want to do that? Well, suppose we have a real value initial condition. Right, so if I require x of z, x of t be located at some point in our phase plane, and a and b are both real numbers, then I'm probably only interested in the real solutions. So my trajectories that I'm interested in are perhaps going to only be the real bits. And so perhaps we're not interested in what's going on in the complex plane. So that being said, we know that the real and imaginary components of our vector x1 are linearly independent. Therefore, we can write a general solution just keeping track of the real components using these two vectors. So I can take the real component, multiply that by c1, and then add that to c2 times the imaginary component. And in this case, I'm just ignoring the fact that this might be complex, right? And because these two are linearly independent, then that is also a solution to the system. Okay, so, and we can generate real value trajectories from these two vectors. Okay? So, for example, if I look at the real value vector here, this vector is essentially telling me two things. It's saying the x1 component is e to the negative t over 2 cosine, and x2 is negative e to the negative t over 2 sine. And we can interpret this essentially as a polar coordinate problem. Okay, so this is like our cosine theta and our sine theta, right? Where these exponential functions are essentially acting like the radius, right? So this is like r1 cosine t, r2 sine t, where these two radii are varying with time. Okay, so let's look. We'll make a plot of x1 and x2 using the real vector. And we'll see what kind of trajectories we get. Well, this is going to be like a polar coordinate problem. And so what I'm going to do is I'm going to start by drawing a circle with the radius of 1 here. Here's a circle with the radius of 1. Okay, and what these two components are telling me is I've got a trajectory that's circular, but the radius is decreasing with time, right? So if I take the limit as t goes to infinity of either radius, as t gets very large, the radius is approaching 0. So initially, if I say start at t0, let's see, what do I get? If I start at t equals 0, this radius term is equal to 1. And this radius term is equal to negative 1. So what do I get is I start out at a point here. Okay, and as time goes on, whoops, I'm sorry. So this should be 1, and this one should be 0. So sorry, this starts out here. So this is at t equals 0. Okay, and as time increases, the cosine function decreases, and the negative sine function increases. So what I'm going to get is a trajectory that looks kind of like this. So you get something that goes clockwise, and then eventually it's going to spiral to the origin. Okay, so initially it starts off almost close to a radius of 1, clockwise, but the radii are decreasing with time. So it's circular with the radius essentially going to 0. So for the real component, this is what we get. So we get a trajectory here that spirals in towards the origin. That just comes from our sort of polar coordinate interpretation of these two vectors. Likewise, we can do the same thing for the imaginary component. So the imaginary component, this is also like our sine of theta, our cosine of theta. Here, e to the negative t over 2 is acting like the radius for both the x1 and x2 components. Okay, at t equals 0, let's see. The x1 component is 0, and the x2 component is 1. So that starts here at t equals 0 for the imaginary component. Okay, and the trajectory that we get as t increases, both of the radii go to 0. Again, we'll get a trajectory that is going clockwise, and it also spirals in towards the origin. Okay, so if we care about real valued solutions, we can generate trajectories from the real and imaginary components of just the x1 solution. Okay, and of course, if we're sufficiently motivated, we can get 2 additional trajectories from the x2 vector from our general solution. So if we go back to our general solution down here, we can do the exact same kind of analysis for x2. We'll get an additional two trajectories if all we care about are the real value solution. So that's what we get from that. So, so in this case, in this example, the limiting behavior as represented by spiral trajectories. Also, the equilibrium solution in this case is different than what we had when we had real eigenvalues, right? This type of equilibrium solution has a special name. This is called a spiral sink. Okay, and it approaches the equilibrium solution, in this case, with spiral trajectories. So, and in this case, this is a stable equilibrium solution. And as you might guess, we might also have trajectories that spiral outward. Now, in lieu of giving you an example, I know you're broken up about this. In lieu of giving you an example of a system matrix that has trajectories that spiral outward, I'm going to cut to the chase here and make an observation. So we'll make an observation. So our eigenvalues for this problem were complex. So lambda 1 and lambda 2 are going to have a real and an imaginary component. The real component of lambda in this case is mu, and the imaginary component of lambda is the value nu. So in the example we just did, lambda 1 was negative 1/2, or let me write it like this. So lambda was 1/2 plus or minus I. So the real component of lambda was negative 1/2, and the imaginary component of lambda was 1 in the example that we just did. So in order to get a spiral sink, it turns out that the mu value, the real value component of the eigenvalue, has to be negative, right? And how do I know that? So in general, you're going to have a exponential function with lambda times t. So you have e to the lambda times t. And we can break this up into the product of two things. We can have e to the mu t times e to the plus or minus I nu t in this case. And this term is what we can apply the Euler formula to. So this is e to the mu t, oops, not function of t, but times t. And this term here is going to be cosine of nu t plus or minus I sine of nu times t. Okay, and whether or not the function spirals inward or outward depends on this term here, right? The imaginary part, or the imaginary exponential, what does this do? Well, this takes care of sort of the repeated oscillating nature of the solution. Whereas this term here, this acts like the radius in a polar sense. So if we treat each of the vectors as a polar coordinate problem, the real exponential controls the radius. Okay, so if mu in this case is negative, then what happens? Well, as time goes on, this function decreases to 0, and you'll get behavior that acts like a spiral sinc, right? This is basically comes from exponential decay. Okay. Likewise, if mu is positive, then we get something where the trajectories spiral outward. In that case, we call this a spiral source. Okay, so this is where the radius of your polar coordinates increases. So we get exponential growth. Okay, so without doing an example, right, if we get something, say we start at 0 and we get something that looks like this with the exact same analysis, we get a spiral source. So the real component of lambda in this case is going to be greater than 0. Okay. Now, and of course, if you're interested, your book has a very nice example starting on page 169, I believe. Okay, what does the new component do? What does the imaginary bit of the eigenvalue tell you? So, the imaginary component of lambda, in this case, is the value nu. And how does this contribute to the behavior of your trajectory? Well, this component, as it turns out, appears in the trig functions, and it turns out that this is the frequency. This is the frequency of the trajectory. Now, this tells you how fast the trajectory doubles back on itself with time. Okay, so if the frequency is large, we have something where the trajectories really double back on themselves very quickly, whereas if the frequency is small, all right, it might take a while for the trajectories to grow. Okay, so that sort of gives you the frequency of the spiral in this case. And we could perhaps see that a little more clearly if we were to, say, draw the component solutions of your solution. So let's look at our example here where we have the spiral sinc. So what we did was we looked at the real component. So we get x1 equals e to the negative t over 2 cosine. And x2 equals e to the negative t over 2 sine. Oops, there's a minus sign here. So we can kind of see where this frequency might occur by looking at the component solutions of, say, just the real vector. Okay, so in the component plot, what we do is we plot one or the other components against time. And we just plot and see what these functions are doing. Okay, so to do this, what I'm going to do, I'm going to start by drawing a cosine function. And let's do this here. So let's say that this is pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and we know our cosine function oscillates between 1 and negative 1. So I'm just going to ghost the cosine function. On here. And let's look at the x1 component and let's graph that on out. So this function is essentially a cosine function. I claim. Okay, but what's happening to this cosine function is the amplitude is changing. So at t equals 0, the amplitude starts out at 1. Okay, but as t goes on, the amplitude decreases. So it is a cosine function. It's going to pass through the same t-intercepts here as the regular cosine function, but as time goes on, the amplitude is starting to go down. Okay, so the x1 solution is essentially looking like this, and if we were to take this out even further, it would eventually peter out to an amplitude of 0. Sorry, I should have maintained the frequency there, but the frequency doesn't change. Its frequency is stuck at 1. Likewise, we could do the same thing for x2. This is like a negative sine function, where the amplitude is also decreasing. So a negative sine function starts off by decreasing. Right? It's going to peak out at pi over 2. It's going to go to 0 at pi. Okay, but the amplitude is gradually getting smaller as time goes on. So it looks like a negative sine function where the amplitudes are sort of petering out. And one way to actually think of this is to almost superimpose your exponential decay function, right? So here is the amplitude at 1 for e to the negative t over 2. And this function is decaying to 0 with time. So our cosine function has to, and let me actually mirror that down here as well. Our cosine function for x1 has to, the amplitudes have to oscillate between these two exponentials. Okay, so we can kind of think of that as the exponential function is attenuating the amplitude of x1 and x2 with time. Okay, the frequency here, of course, is 1, and so that controls how many times the cosine or sine function cross the t-axis for a period of, say, 2 pi. Okay, in this case, this is what we get for a frequency of 1. Okay, and this might be a good time to do a little bit of review of plotting your trig functions and how perhaps the frequency can affect how the function repeats itself.